Hey, it's Mathman Dan. We are in Warner Springs, California. I'm here with Brett at Sky Sailing, where they operate sailplanes, gliders basically. And we have one of the fanciest ones behind me here, but you have a whole fleet of Skyplanes. And you were telling me that there's all kinds of math involved in getting these things up in the air. Way more than people might expect, actually. But for starters, there's some math you have to do before it even gets off the ground. So you were telling me about how you have to shift people around sometimes. What's going on with that?
Well, you have to understand that most of aviation is math. It's applied mathematics because everything we do is thinking in angles, it's thinking analytically, so a lot has to do with math.
Sounds
but
good
we
to
also,
me.
that's right, and it is applied math. But now if we look at the center of gravity of an aircraft, all right, we have to have the aircraft has to be in balance for it to be able to fly.
Okay.
So if we have this center of gravity in the wrong spot, it could be dangerous. So we have a range, let's say, of where the center of gravity has to be inside this range. If you fall outside of that range, you might not be able to get the tail of the aircraft up.
I see.
If you're aft of it, you might not be able to get the tail down. So you want to be able to fly this aircraft correctly. So now we have to take the weight of the aircraft, the empty weight of the center of gravity of that aircraft, the weight of each of the passengers, and now we got to figure out if that person, there are a certain number of inches aft of datum. So now we take that measurement, that weight, and we look at maybe they don't weigh enough. So we have to add lead, or take them out to a big lunch, one or the other. So we can add weight to that person. In America now, that's usually not a problem, right? So we might have to switch seats. So we have to have this thought, we have to calculate it and make sure that the aircraft can fly safely.
Okay, makes sense. Now, once you're towed up in the air and you're on your own, you were telling me there's all kinds of angles involved.
Correct.
And you also have a measurement for how the plane's going to glide downward, for example.
Correct.
So my algebra students might be a little familiar with this idea. You guys had other terms for it, though.
We have different terms, instead of x's and y's, and we use lift over drag. The lift over drag ratio, L over D, is a ratio, and that gives us an angle. For instance, this one has a 50-to-1 glide.
And this is one of the most efficient
This is very
planes,
efficient.
right?
Well, it's not the most, but it's a very
Close.
efficient aircraft. Yeah, it has 76 feet of wing.
Wow.
Right? That's a 23-meter aircraft. So we
That's
do a lot of
huge.
meter, too. All right. And we have this L over D of 50-to-1, which means for 1 foot down, we'd go 50 feet before it would touch the ground. So
Which is amazing to me.
it's
that it
very,
does
very
that well.
flat. It's
So
very flat.
if you're a mile up in the air, you should be able to go 50 miles
In any
out.
direction, so you've got a 100-mile radius to work with.
That's amazing.
A 100-mile radius. And that's only from 5,000 feet up.
You can do that, no problem?
Yeah, there's nothing to that. That's easy. That's easy.
So my algebra students, they would know this as slope, basically, was what it is, and they might call it rise over run. So in this case, they would say the slope is 1 over 50.
Right.
Same exact idea.
Right. But now we're going to throw in something new. Now, you're just working with slope, rise over run going one direction. Well, what if we add wind?
Okay, so that's going to affect you, right?
It's going to affect you because your headwind is going to slow you down. While a tailwind's going to speed you up. It's going to change your glide. It's going to change your glide angles. Also, we're working with nature. So we have lift and we have sink. Lift is what we look for because a sailplane's always sinking. It's always going down at 200 to 300 feet per minute.
That's that glide ratio.
That's the good. Well, it's not even. It's the sink rate. It's how fast it's going down following that glide, right? And and we also have the speed that goes along with it that we're going to be tracking. So we're three-dimensional. We are three-dimensional. So now we find a thermal or a rising current of warm air, which is usually found over City Hall, but we don't have City Hall out here. So if we find this rising current of lift or thermals, we would circle in that lift and climb. Now sailplanes have climbed to over 50,000 feet. That's
Just
higher
using
than an
these
airliner.
thermal-
Well, not thermal, that one's actually using wave, a little different.
Okay, but by taking advantage of the natural winds out there, you can actually cheat the lift over drag you told me about,
Right.
get some extra mileage out of it.
Yes.
All right. That
And
sounds...
you can go, how long can you stay up? How long's your bladder good for, right?
I don't know.
They stopped keeping that record. There is no longer any record of duration because after 40, 50 hours, you're not proving anything.
In theory, you could take advantage of the winds.
Correct.
And be up there for a long, long time.
Correct.
Now, you also told me that in addition to just the vertical angles we were talking about, there's other angles you have to consider when you're just trying to navigate and maneuver.
Well, anytime you're going anywhere, you're thinking, well, am I within glide range of this airport? Am I within glide range of, you know, if I've got an airport here and I've got an airport here, how high do I have to be in order to transition from that airport to this airport? Because I've got these angles, and they're going to be different because I have a headwind or a tailwind. A sailplane moves completely with the air mass. So let's say I'm flying at 50 miles an hour.
Okay.
And I'm flying into a headwind of 50 miles an hour. How fast are we going over the ground?
You should be hovering, right?
We're 0 ground speed.
My algebra students have word problems kind of like this,
That's
but yeah.
But if you turn around, we're doing 100
Right.
over the ground, but we're still only flying at 50 miles an hour.
So
now we have to translate all this into getting us someplace.
So you are having to constantly reanalyze what all the surrounding speeds are doing, the wind speeds, and then the speeds your plane naturally is going to do.
Correct.
And then you also told me that when you're finally going to come in for a landing, I know there's fancy instruments, but the pilot should be able to do everything even if the instruments don't work.
We don't need any instruments. We don't need no stinking instruments. Because when we fly, here's my runway or Farmer John's field, whatever I'm going to have to land in.
Okay.
All right? Now, I want to come in on a 45-degree angle so that I would bisect the runway in the center on a 45-degree angle. I come in, then I turn downwind, so I'm paralleling the runway. I want to be 600 to 700 feet out on probably a 30-degree angle down, and so that I'm flying parallel to the runway. And then out off of 45 off the end of the runway, I'm going to probably be making my base leg, and then which is going to be perpendicular to the runway. Now I'm turning final, so that I'm lined up on the runway. But this is three-dimensional. Not only am I a distance away and height, it varies. It varies with where I am, what the situation. I can't add an engine, so I've got to work. So if I'm low, I'm going to turn earlier. If I'm real high, I might go out further. But once we get onto base leg or so, we have this wonderful thing called spoilers. And what the spoilers do is they create a loss of lift in that area and makes the sailplane sink. So when I'm coming into land, I want to come down at a certain angle so that I get to the ground, round out, touchdown right where I want, every single time. But the winds are going to vary, your height's going to vary. So I have to think in my mind, what is the angle that I want to be following at a half spoiler? Why do I want half? So I can get rid of it and glide flatter, or add more spoilers and glide at a steeper angle.
And a nice, smooth landing.
Nice, smooth landing.
So really, coming in, it's much of what's going on is the pilot analyzing angles as they steer the plane.
It's all angles. It really is.
That's good to hear. Now, I know earlier you actually showed me a book, and inside there was some actual equations, maybe I can show those later, and some graphs showing, for example, different angles you can set the plane at and the speeds you can attain. So maybe in the studio I can show afterwards some of that math that you showed me earlier.
Yes.
Brett, I just have one last question for you. Can I borrow this for a little while?
Anytime. Anytime.
Thank you so much for sharing a little mathematics in sailplanes for us today.
It's math. The world works by math.
I know. I try to convince people.
Well, you know, it's hard because they're in the class doing these figures. They don't realize, you know, real world uses math.
There's a lot of mathematical thinking that goes on.
Thinking.
Yep.
It's analytical thinking.
All right. Thanks a lot,
My
Brett.
pleasure. You guys listen.
Back in the studio, we'll do some more of this. I'll show you guys. Well, this is the only sailplane I actually took away from there, but as you did see, I got to have a ride, which was really fantastic. And I don't know if you noticed that sailplane we were in was a special one. It has a propeller, so it actually propels itself up in the air. It doesn't have to be towed, and then you just cut the engine, the propeller kind of sucks back in, and you're on your own. So we just glided all the way down, no power at all. That's on Warner Springs, and if you know, he mentioned several, our friend Brett there mentioned several different aspects of mathematics. I was going to show you a little follow-up on a couple of things he mentioned. So for starters, he talked about center of gravity. So this is actually based on some fairly simple algebraic equations, and I have one up on my screen right here, so you can, this is like a, actually on my computer, so that's a printout. We'll go to that in a second. On my computer here, we have, what I've drawn is, well, a primitive, this is primitive, right? I've drawn a seesaw. Remember those when you're a little kid? So I have drawn a little teeter-totter basically, and this is the exact same idea that he was talking about with the center of gravity. Basically, if you want this to balance, the teeter-totter, what is called the moments on each of the two sides has to be the same. So for example, I have a 160-pound adult on the right, that's represented by that blue box, and on the left, I have a 50-pound child. And for them to actually balance on a seesaw, the adult would have to sit closer to the center and the child would have to sit farther out. And you can actually figure out exactly where they would have to sit to make it balance with a simple mathematical equation. So we actually showed that during our interview with Brett, but here I have written it again. And a simple computation here, if you were to solve this one, it would become 480 over 50, which is 9.6. That's how far away the 50-pound child should sit to make up for an adult 160 pounds is only 3 feet away from the center. So what you can do is you can adjust where the center is by the placement of the different weights, and this is basically what happens in the airplane. You don't have just 2 weights though, you have several, and you have to consider the weight of the plane itself, and then you can move certain things around to make sure that the center of gravity shows up within an acceptable range. You don't have to be exact, but it has to be close enough, otherwise the plane is not in balance and, well, it won't fly. So on my math cam, I actually brought, he was nice enough to Xerox a couple pages, write out some training materials they have, and that's what this is, and you probably can't read that. Let me zoom in a little bit. This is basically what someone learning how to sail planes would have to learn, and if you look at, there's weight, and then it says arm, that's the distance, and then it says moment. If you multiply the weight by the distance or the arm, you get the moments, and basically the moments all have to add up to balance to be where you want. Here's another illustration at the bottom of this page here. I'm going to scroll down there. This is a plane, and it's marked up with lots of different spots where they would have to worry about what's causing the center of gravity to be where it is. So again, something they have to keep in mind as they go through preparations. That's before they even get up in the air. Another thing he mentioned I was going to show you was he talked about the glide ratio, and I mentioned this is based on slope, and it really is. So a very simple example, the nice plane I got a ride in was, he said, was a 50-to-1 glide ratio. So he would actually write it like this, 50-to-1 glide ratio, and if you watched my interview, we had a nice illustration of what this is talking about. In this case, the 50 actually refers to how far horizontally you will glide, so we had something like that. And the 1 is a vertical measurement. I actually drew the arrow down on our interview because if you're in math class, you would consider that a downward rise, if you will. So this is very similar to what you would see in an algebra class. He's forming a fraction, basically, a ratio. In algebra class, we usually do rise over run, and we call it slope. Well, in this case, the rise over the run, the rise is actually negative, -1, and the run is 50. So we would say that the slope is -1 over 50. And that's how the plane, I'll draw it here, would actually glide down. That's the angle that's rated for the plane. Now, all the planes had different ones, but that particular plane was quite efficient. So he also mentioned that wind speeds affect this, and he gave me some other materials I was looking through. And I was trying to investigate the math involved, and if you actually were going to take some lessons and learn how to fly a glider. And one of the things he showed, I'm actually going to write out exactly what I saw in his materials, and I want you to see if you can figure out what's going on. So the story is, let's say we have a plane that glides horizontally at 65 knots. They usually measure them in nautical miles. But you have a 15-knot tailwind that's going to push you faster. So here's a typical example of what I saw here. He had a computation like this. So I saw something like 50 over 1. This is the glide ratio. So remember, that's similar to slope. And he had that multiplied by the strange-looking fraction. I want to see if you guys can help me figure out what this is doing. He had 65 plus 15 on the top and 65 on the bottom. what exactly is that fraction doing? And then he multiplied by the altitude. And the idea behind this was the glide ratio times the altitude tells you how far you can go horizontally. So 50 times your altitude, let's say is 4,000 feet, that'd be 200,000 feet horizontally, you could glide before you're going to touch the ground. But then he has this extra fraction in here, and if you think about what's going on, the only thing we have to worry about is this is actually changing your glide ratio. In fact, this itself is about 1.23. What this is doing is it's making your actual speed a little faster, because on top of that fraction is a 65 knot plane speed, and it goes 15 knots faster from the wind, and then you're dividing by your original speed. This is like a multiplier to figure out how much faster your glide ratio is going to be pushing you. So in this case, you could say it's 23% increase in your horizontal distance you can get. It's actually going to change your glide ratio. And by the way, the next part in his materials that I saw said something like this, 61.5 times your altitude. So what he did was he combined that fraction with the 50/1 and figured out that, hey, our new glide ratio, because the wind is helping us, is now 61.5, and you can use that to estimate how far your distance can be before you're going to have to find an airport or a nice field, as he mentioned. A couple other things he talked about. I said I saw some graphs in his materials. I was going to show you a couple of those on my math cam here, just so you can see all the math that showed up, and flying these planes. So this here, let me zoom out a little bit. I don't know how well you're going to see that on your screen, but this is actually a sort of a shortcut they have for the center of gravity. It has some recommendations on the graph of how much you can put in the front and how much you can put in the back to make sure that the center of gravity comes out right. He has another graph. This looks really something somebody might see in a math class. There's a grid and some nice curves drawn, and these are performance curves, which are under different conditions. I don't know if you can see, it's pretty small, but right here it says L/D. That's the glide ratio we talked about, lift over drag, very similar to the slope. And this is, if you can read the graph, he's showing you different adjustments for what glide ratio you can expect under different conditions. One more graph for you. This one, a little harder to figure out, but I just wanted to show you an example of how these things actually show up in maybe places you wouldn't expect. This is called the flight envelope, and this is basically the center of this area here, this kind of strange shape you see. This is the safe area for your plane handling the G-forces you can put on it with these things. And the planes, even though they're not powered, they can get quite a bit of G-force, depending on what the maneuvers of the pilot is doing. And I actually experienced a little bit of that myself when I was going for the nice ride, so I can attest to that. So anyway, a graph that shows you visually, under different settings, what's safe. And then you saw some shaded area in the graph that said, like, hey, you better not be here unless you're really careful. So we had a camera crew in Albuquerque, New Mexico, filming their hot air balloon festival, and wouldn't you know it, there's some math involved. So first, check out some of the gorgeous scenery and all these crazy balloons. So by the way, Albuquerque, this is the world's largest balloon festival, and they can actually get over 700 balloons in the sky. So we're going to show you a little bit of how these things float through the air. And yes, there's some math involved. The first thing we have to start with, though, is I have to convince you to think of air kind of like water. So when you throw something in the water, and if it's lighter than the water, it floats, and if it's heavier than the water, it sinks? That's kind of what's going on here. In fact, this all leads back to a guy named Archimedes. The Archimedes principle says if something's floating in water, then the force pushing it up, making it float, is equal to the amount of the water displaced by the object. So in other words, kind of like gravity is pushing stuff down, but it's called the buoyant force, it's pushing it back up. So what we're going to do is try and convince you that air works exactly the same way. So if you can think of air in that sense, then what we have to have happen is you have, this balloon that you'd like to float, and somehow you need to make it lighter than the air that it's sitting in, just like something lighter in water would float upward. So how are you going to make that happen? Well, you might have seen, little party balloons are filled with helium, because helium's lighter than air, sure. But this is not filled with helium. These are filled with normal old air. So we got to figure out how they make these things lighter than air and float upward. And I know it sounds funny, lighter than air. You might think air has no weight. It actually does. Not much, but it has a little bit. And gravity is constantly pulling on that air gently. So actually, if you're on the surface of the Earth, the air is more dense. And if you climb up a mountain and the air gets thinner as you go, you can probably tell if you ever do that. You can tell by the way you breathe. So that's because the molecules are being pulled closer down by the gravity, and they're a little bit denser down at the bottom. All right, so how are you going to make a balloon lighter? Somehow you need to make the air inside lighter than the air outside. Well, they do it by heating the air. So if you've seen balloons, you've probably seen the flames going up. In fact, actually I brought a picture with me. I'll show you what this looks like. Hold on. First of all, this is Archimedes, the guy that came up with that principle of buoyant force I told you about. He looks pretty happy there, doesn't he? These are the burners on a balloon. So these are actually propane. They fire up, and now here's a picture of what they look like when they start firing and shoot flames up inside the balloon. So that's how they accomplish this. They heat up the air, and it makes things, rise. And everyone knows heat rises, right? Hot air rises. But why? Well, here's where the math comes in. Okay, so if you open up a physics book, you will find this equation I'm going to show you now. And it's called the ideal gas law. This governs any gas, including air, which is a mixture of gases. It says PV equals nRT. What the heck does that mean? Well, P is for pressure. The V is for volume. N is, roughly speaking, a way to count how many molecules of air you have. That accounts for the mass or the weight of the air. R is a constant that makes the equation work out correctly. And T is a temperature measured in a certain way. So I'm going to give you an alternate form of it there. This is a little bit simplified and rearranged so we can factor in density to the picture. So in my alternate form, this guy right here, P is pressure, K is a constant. That's just to make the equation work correctly with the numbers we get out of nature. D is the density, and T is the temperature. So below that, I've rearranged it just a little bit so you can see how the relationship is. And so what I want you to think about is, you've got a balloon full of air, and we're going to start heating it. Well, the pressure can't change because the pressure inside the balloon, basically if you increase the pressure inside the balloon, then it's just going to push air out the bottom of the balloon. If you decrease the pressure, the balloon would actually start, sucking inward and you wouldn't have the full balloon. So you can assume the pressure is going to stay the same. So that's not going to change. The constant below, that K number, that's set by the equation. That's not going to change. The only thing you could change is the temperature. So what I want you to think about is, what if you take this temperature and you increase it? What's going to happen to the density in this equation? Well, if you take a fraction and you make the bottom bigger, that means the whole fraction overall gets smaller. So if you increase that value T, that necessarily is going to make the density decrease. Okay, well, again, you could say, so what? Why does that make the balloon go up? Well, if you decrease the density, that means the air molecules are actually farther apart from each other. And in fact, this is what happens. When you heat air, basically you're transferring some of that energy in the heat to the molecules. They start vibrating, sort of hitting up against each other with more power, and it creates more space between them. So now you got to imagine you got a balloon full of air. In the same amount of space, you now have fewer air molecules. This equation tells you how it's going to work. If you have fewer air molecules, that means there's overall less weight. It's the collection of those molecules that creates the weight of the air. So the hot air expands, some of it gets pushed out at the bottom of the balloon. There's actually, in a sense, less air weight in there for the same amount of space. That means it's lighter than the air around it. The buoyant force Archimedes talked about then pushes the balloon upward. It's almost like gravity's pulling the cold air down, and that is sort of forcing the balloon out of its way. The cold air wants to get down with more thrust than the hot air is resisting, so it gets pushed upward. But here's the thing. How much do you have to heat up your balloon? Well, the balloon itself, you can't just heat the air and make it rise. You have to heat it up enough to lift everything up. The balloon itself typically weighs about 800 pounds. Put a pilot and 2 humans in there, added what, an extra 400 or 500 pounds. You've got to lift quite a bit of weight. So that's why the balloons have to be so large. In fact, if there's time later, I have another equation I'll show you that shows you how to compute how much space you need in that balloon. But just to give you an idea, a lot of those balloons are 7 stories tall. It's pretty sizable, just to carry a little basket of people, right? There is actually some math you can work out to see how big the balloon has to be or how hot the air has to be inside to lift up what you need to lift up. And the balloons do come in obviously different sizes, but the standard one I mentioned is kind of 7 feet tall. If you went for a balloon ride, that's probably what you have. They're about 55 feet across. And I mentioned they weigh 800 pounds. And then you add some people onto that. And actually there's some weight inside the balloon. I mentioned the air actually has some weight to it. So you have to lift up quite a bit of weight with this balloon, and that's why they have to be so large. Well, I have a little equation that on my screen here. This is kind of a rule of thumb equation that somebody worked out. And it's basically dealing with air pressure at sea level. And you know, it gets a little technical because if you're at different locations, then the air has different weights and pressures. But this is just sort of an approximate way to look at it. And what I have labeled here is this T0, this is the outside temperature. That should be the air surrounding the balloon. And then the TH, that is the heated temperature inside the balloon. This equation will actually figure out for you how much total lift you get. And that lift would mean how much force the balloon's going to get pushed up with. And that will determine if you can actually overcome gravity and get the thing off the ground, lifting up your hundreds of pounds of people and everything else. So I thought we could do a little example. I looked up some statistics here of these balloons, and well, tell you what, let's just work out an example first, and I'll tell you how big the balloons are as far as the air temperatures are concerned. So let's say, by the way, they like to do the balloons in the morning because the air is cooler, and that means if you heat up the air, there's more of a difference. So let's say it's 65 degrees outside on a nice morning. You go for a balloon ride, and the person in the balloon, the pilot, heats it up 100 degrees beyond that. If we put all those values in, let's see how much total lift we get. So this would be 635. I mentioned it'd be 60 degrees outside, so 60 degrees here plus the 460 minus, okay, now I said we were going to heat it 100 degrees. That means that the air inside would be 160. And again, this is a little bit approximate because in reality, you know, some of the air in the balloon would be warmer at the top than the bottom and all that, but just as a rough idea. If you work out this number, it comes out to be pretty small. In fact, this is about, it comes out to be 0.1935. Well, I should tell you that these are measured in ounces, and this is for 1 cubic foot of air. So imagine 1 cube, 12 inches on each side of air. This is how much lift you're going to get for that amount of air. And roughly speaking, that amount of air weighs about an ounce. So this is basically telling you you're going to get like 1/5 of an ounce of lift out of this piece. So this explains why a balloon has to be so large, because 1 cubic foot of air is only going to lift that tiny amount. Well, imagine that you have 800 pounds of the balloon and people and everything else, and you want to lift all this stuff up. How much would you actually need? Well, I looked up, you know, a typical balloon. They tend to have 90,000 cubic feet in them. That is about, I figured this out actually, I think it's about 673,000 gallons of air in these things. So if you take 90,000 cubic feet and figure out this many ounces for each one, I did it ahead of time luckily, it comes out to be 17,000 ounces. And if you divide by 16 ounces in a pound, it comes out to be about 1,100 pounds. So heating up 100 degrees, you could actually lift about 1,100 pounds, which would be enough for the balloon and a couple people. But they probably actually heat up even more than that, probably heat up 120, 130 degrees to get all that lift. So then the question is, because you're believing me on how this works, right? How you get the balloon up in the air. And then the question is, how do you get back down? Well, you could just sit and wait for the air to cool, but it takes a long time. So actually, they have a flap in the top, like an escape valve. They can actually pull some wires, and it opens up some holes in the top of the balloon to let some of the hot air out, suck some cool air in from the bottom, and then you can cool it down that way. And the more air you let out, of course, the cooler it gets inside, and you can slowly drift down to the ground like you want. In fact, I actually have with me a picture of the top of the balloon. You can see in there, the blue part is the sort of the escape hatch, and there's some wires attached there, and if they pull on those, you can open up the escape hatch a little bit and let some of the air out. You kind of control it, you know, how quickly you want to come down. All right, just a little trivia about the balloons. 1,800 square yards of nylon fabric to make those things, and 3 miles of thread. So I guess they're not cheap to buy, huh?